Hello, class. This is Mr. Hart, and in this podcast, we want to start the chapter on earthquakes. And this is a really fun chapter. We get to look at some interesting earthquakes that have occurred in the past and look at some of the mechanics of earthquakes. But let's get right into it. Before we can start anything with earthquakes, we have to understand why they're occurring and some of the different types of stress that the Earth's crust can have, which causes these earthquakes. Okay, so you might just think, well, force is force. Stress is stress, like this rock here. It's just obviously had some fracturing occurring, some breaking that's occurring. And you might just say, well, the rocks are pushing on each other. Well, we want to be more detailed. There's actually lots of different types of stress that can occur on these rocks that can cause earthquakes. So let's look at a couple of different ways that there can be stress in the Earth's crust, this, force in the Earth's crust. Okay, so there's a couple of different types. There's confining stress, there's compression, there's tension, there's shear, and then there's strain and deformation. And then that can be actually broken down into three groups of elastic deformation, plastic deformation, and fracture. Okay, so you're going to want to know all these terms. Okay, but let's go through each one and kind of see what they mean and how they relate to earthquakes. Okay, the first type of stress is what we call confining stress. So if you've ever been in an elevator that's overcrowded and people are, stuck shoulder to shoulder, and you feel claustrophobic, then you may understand what confining stress is, okay? This is when you have a rock that is deeply buried, okay, and is pushed down by all the weight above it, okay, all the material that is above it. And since the rock cannot move, it cannot deform or lose its shape, okay? So think of like an elevator crowded with people or like being at the bottom of a dog pile, right? It's not that you can't or that there's someone pushing on you constantly or you're constantly being forced in a certain direction. You're just kind of stuck, right? You are confined. You can't move. And so rocks under confining stress are basically at the bottom of a dog pile is what you can think of it, right? They have all this pressure pushing down on them. Okay, so let's say you have some rock down here and then you have a whole bunch of layers of rock above it, okay? Well, that rock down here has to handle all the weight of all the other rock pushing down on it, right? So it's kind of stuck. It's kind of being pressured on, and it can't move really. This doesn't cause earthquakes because there's no deformation, there's no movement. Okay, but this type of stress can change the rock. If you look over here, you can kind of see some of the rock is this nice, gray color, and some of it's this tan color. Well, that's because part of this rock has had that confining stress on it, and you start to get different chemical properties occurring because of all this different stress, and so it can change the rock itself. This type of stress, though, doesn't generally cause earthquakes. Okay, but again, confining stress is pushing in on the rock. Okay, the next type is what we call compression. Okay, and compression is when you squeeze rocks together or pushing rocks together, which causes them to fold or to fracture, which basically means they break. Okay, and like you would expect if you remember the plate tectonics chapter, compression is most common with a convergent plate boundary because you have the two sides pushing in. Okay, so if you look at this valley right here, you can probably see these nice fold lines going through the whole valley right here. Okay, and this is good evidence that there's some compression going on because generally what that means is that you have some type of pressure coming from if this is facing north, the north side of the valley, and some type of pressure going in from the south side. Okay, you can kind of imagine if you took a stack of papers. Okay, here's my stack of papers right here. Okay, and if I pushed on them from the sides, well, what's going to happen if I take that stack of papers and push on it? It's not going to, just compress nice and evenly throughout the material. It's going to actually bend and fold in order to compensate for all that new force on it. Likewise, if you look at this picture, okay, this valley is bending and folding because of this compression on the sides. Okay, so that's what we call a fold. Okay, sometimes if there's enough pressure, you're actually going to get a fracture, meaning the rocks are going to start to break, and that's when you start to get earthquakes. Okay, and again, this is what you'd expect with the convergent boundary because convergent boundaries naturally are doing this, right? They're pushing in on each other, okay, from the side. Okay, so that's compressional stress associated with a convergent boundary can cause earthquakes if the rocks fracture. Okay? Then the next type of the next type of stress is what we call tension. Okay? And what that means is that the rocks are actually being pulled apart Okay, and they will either lengthen or break apart. And again, tension is the major type of stress of the divergent plate boundaries. Okay, so if you look at this rock right here, you can see this nice white line right here. And you can imagine that this rock is being pulled apart. Okay, just like if you took silly putty and you kind of stretch it out, okay, you're pulling on it from the sides and it's starting to pull apart. And so we can see this new exposed surface that wasn't there before because the rock is actually, stretching. Now, in some cases it will stretch, in some cases it will actually break, just depending on the structure of the rock. And if it actually breaks, then again you get that fracture, and that movement's going to cause an earthquake, either big or small, but it probably will cause an earthquake. And again, this is associated with a divergent boundary. Okay. Then the next one is what we call shear. And you may be getting the pattern by now. This one's associated with a transform plate boundary. What that means is you have forces that are parallel but moving in opposite directions. Okay. This is what you usually associate with a fault line. So you have some type of movement this direction, some type of movement this direction, and they're going to kind of slide along each other. If you take your hands and rub them together, okay, do that motion, you can feel heat building up, right? Well, in the case of these types of rocks, they're actually going to have, again, vibrations, what we would associate with heat in our hands. That's going to be vibrations in the rock, and again, as they slip and slide, they're going to cause earthquakes. Okay, but this type of stress, again, is called shear, this pulling in opposite direction, what we associate with a fault line. Okay, and then the last type we call strain and deformation. And so this is kind of an interesting type. Basically what happens is the rock itself is being deformed, meaning it's changing its shape. And under certain circumstances, you can get specific types of movement. Okay, so that's why we have these three categories. We have elastic, plastic, and fracture. So elastic deformation means you have some stress on the rock, but when the stress is removed, the rock's going to return to its original shape. Okay, so the rock returns to its original shape when the stress is removed. Okay, imagine, for example, flexing your muscles. If you flex your muscles, right, they change shape, they get stressed out, right, which causes them to bulk up. But then when you relax your arm, right, then that muscle then relaxes as well. It returns to its normal shape. Okay, it doesn't stay flexed once you put the stress on your arm. Okay, it doesn't stay flexed. Once you relax, it's going to return back to its original shape. Okay, so that's elastic deformation. Then there's plastic deformation, where you put the stress on the rock, but the rock does not return to its original shape when that stress is removed. Okay, so maybe you've heard that phrase that your mom always says, like if you put your face, or you put a funny face and you keep it there too long, then it's going to stay that way, right? If you have a funny face and you keep it there, it'll stick. Maybe you've heard something along those lines. Okay, that would be an example of a plastic deformation if it was true, right? You put your face in that weird configuration, and then if you keep it there, once you try to relax, it's going to stay that way. Okay, obviously it doesn't work like that, but that's an example you could associate with plastic deformation. Okay, so once it goes into that shape, when you remove the stress, then it's not going to go back. Okay, and then the last example is fracture, where there's so much stress that the rock will actually break, again, usually causing an earthquake. And so you can think of like popping a balloon, right? You put a pencil into a balloon, at some point, it's going to be elastic deformation, right? If you remove the pencil, it'll go back to being a balloon. But if you push too hard, then that balloon's actually going to fracture and break. Okay. So if you look at this graph, usually these three are not, disconnected. They're actually often for the same rock, but we have to look at the different levels. So if you put just a little bit of stress on a object, it's just going to have a little bit of strain, and it's just going to be in this elastic region. So it will probably return back to its normal shape when that stress is removed. If you put more and more stress, then you'll get more and more strain, and you start to get to the point where it's the plastic deformation, and it won't return back to its normal shape once that stress is removed. And then if you get too much, then that's when that actually fractures, and you usually get an earthquake. Okay? So hopefully that makes sense. And sometimes you can even get earthquakes with elastic deformation if there's quite a bit, if the rock can stretch quite a bit and move quite a bit, and that stress is removed. When it moves back to its original position, you can get actually some large earthquakes that way as well. Okay, but as you put more and more stress on the rocks or whatever it is, okay, you're going to get into the elastic, plastic, and then fracture for your deformation. Okay, so those are the different types of stress. Okay, so make sure you understand what all these guys mean and what they're associated with. Okay, let's cover two more topics. The next topic we want to cover is what we call folds. Okay, we kind of looked at this with compression, but this is the idea that rocks will tend to bend when they have that pressure on them from the sides. Okay, so you can kind of imagine that this rock had some type of compression coming in from both sides, causing it to fold to compensate for that. And so whenever you have that compression, you'll get these folds in the rocks depending on the material. Okay, but there's actually two different types of folds we want to look at. Okay, one is a syncline, where it bends downwards, okay, downwards from the center, and then there's anticlines, where it bends upwards from the center. Okay, so I would have those two vocabulary words written down. You don't have to write it the same way, but the syncline is basically the fold that bends downward from the center, and anticline is the fold that bends upward from the center. Okay, and you don't always get these two separated. Sometimes you can get them one after another. So you could have an anticline followed by a syncline followed by an anticline. Okay, you can actually have lots and lots of them in the same area. In fact, here's a picture an example we did in class with this picture. How many folds do you see in this example? Well, you can find quite a bit. There's one kind of going right here. There's one going up here. You can kind of see one down over here. Probably one kind of in this direction. There's one over here. One over here. So there's probably at least 6 or 7 folds in this picture, all kind of associated with each other, all in the same area, just based on how the rocks were compressed over time. And so they're not independent. It just depends on that compression again, where the compression is coming from. And so we will understand those different types of folds. Okay. And then the last thing we want to cover is fault lines. Okay. So we've talked about faults quite a bit when we talked about transform plate boundaries, because all transform plate boundaries tend to be faults, but not all faults have to be transform plate boundaries. Okay, so let's look at some of the other types of faults that we're going to have. But before we do that, let's look at some of the vocabulary we need to know. Okay, so we're going to want to know what a joint is. Okay, a fracture with no movement on its sides. Okay, a fault is a fracture with movement from rock structures on its sides. And then there's the slip of a fault, which is the distance the rocks move along a fault. And then there's the dip of the fault, which is the angle of a fault relative to the ground. Okay, so take a moment, pause this video, and write down these vocabulary words if you need them. Okay, well, let's compare a joint to a fault. Okay, so a joint is a structure that doesn't have a fault line associated. It kind of just starts to crumble away because of things like erosion, gravity, okay, just natural effects, but there's no fault line here. Obviously, the rock has fractured and changed shape, but it's not because of movement along its sides. Okay, but then there's a fault where we can see, if you look here, there's this nice line going through the center on this picture, and these rocks are actually sliding relative to each other. And you can see right here, if you look at this kind of layer, you can tell that it used to be right in line with this layer right here, but it's kind of slid down over the years. Okay, so that movement, that fracturing that's occurring, is because of the movement of the fault line. Okay, so we want to understand that's what we call a fault. Okay, this is not a fault, right? This is just a joint. There's fracturing in both, but the fault has that line of movement associated with it. Okay, then we have the slip and dip. Okay, which are kind of funny terms, but they kind of make sense if you look at it. So let's say we have that same shape fault. Okay, so we have a kind of a triangular shape here, and we have the two faults, one on top of the other. Okay, the slip is this distance that the fault moves when it starts to slide. Okay, so if you look at that, that's called the slip of the fault. Okay, and then this angle right here, how much the angle is starting to dip, kind of relative to where the ground would be. If you imagine a flat line across the top, this angle right here of how far down it's going is the dip of the fault. Okay, and so there's the dip and the slip. Okay, they're really important for describing these types of faults, because if you have a larger dip, you're generally going to have a larger slip because it can move faster when it starts to slide. Okay, but you want to understand what these terms mean. Okay, if you hear those words associated with a fault, then you know what they're describing with this fault line. Okay. All right, and the last thing we want to cover is the different types of faults we can see. Okay, there's the ones we've been drawing, which we call a normal fault. Okay, so a normal fault just has a hanging wall. okay, and a foot wall meaning one part on top, one part on bottom. In a normal fault, the hanging wall starts to slide downwards, okay? It's sliding downwards relative to the foot wall like you'd expect from gravity, okay? Then there's a reverse fault, or what we call a thrust fault, where you have the hanging wall, you have the foot wall, but because of some type of movement or compression, the hanging wall is actually going upwards relative to the foot wall, okay, which is opposite than what you expect, right? You expect the hanging wall to kind of slide down, but there's some movement on this side, or maybe some movement on this side that is causing the hanging wall to go upwards, okay? And then the last type of fault is what we call a strike-slip fault. Two of them are shown here. You don't have to know the difference between sinistral and dextral, okay? Just understand that a strike-slip fault is what you would associate with a transform plate boundary, okay? So the other two are from a side view. This one's from a, I think that's supposed to say plane view of the Earth's surface, okay, like an aerial view. So if you were looking at the ground, this is what you'd see. You'd see one part of the Earth going this way, one part of the Earth going this way, okay? That's a strike-slip fault. This is what we associate with like transform plate boundaries, okay? So again, all transform plate boundaries are going to be strike-slip faults, but not all faults are transform plate boundaries, because some faults are these guys right here, the hanging walls with the foot walls, okay? But let's just review quickly. So we looked at the different types of stress that we need to know. We looked at how folds happen and what the different types of folds are. And we looked at faults and the different types of faults. Okay, so hopefully that all made sense. Let me know if you have any questions, and thank you for watching.